Next, we have Rebecca White from USC presenting on Event Horizon Telescope data and open source methods.
Hello, I'm Rebecca White. I'm a second-year undergraduate at USC. I'm a computer science, physics, and astronomical engineering major, and I have previously worked with the LIGO consortium, which involves black holes and neutron stars and other astrophysical phenomena like that. So my topic today is basically the Event Horizon Telescope data and basically a reproducibility study that I've been doing with people from University of Tennessee, Knoxville, to basically see if we can get the same data that they do from open source methods. So basically the overview of my presentation today, is basically I'll do a quick introduction about, basics about what is a black hole, what is the Event Horizon Telescope collaboration, the goals of this project, as well as the progress that we've done, our current results, and then our plan for the future. So basically, what is a black hole? Well, black holes are basically astrophysical phenomena that have such an intense gravitational pull that not even light can escape them. There are different types, but the ones that we're concerned with right now are supermassive black holes, and they can be formed by the death of a supermassive star. And not much is known about them because it's difficult to get any readings from them, just given we know that they're there based on everything else that's going on around them. However, it's difficult to directly image a black hole. So we have to search for these things called the event horizon, which is basically the surface of the black hole. And it's basically where the escape velocity of the gravity of the black hole is greater than the speed of light. So what the Event Horizon Telescope does, next slide, is basically is able to see able to see the supermassive black holes. And they have had a single picture of one, and that was the one that was in the news not too long ago of, we finally imaged a black hole. So basically how the Event Horizon Telescope array works is that it's an array of telescopes all around the world that act like an interferometer, and they can basically measure this event horizon. Each interferometer has slightly different parameters based upon where they're located, just, heat parameters and based on everything like that. And putting all the data together, we can get an image of a black hole. So next slide. Yeah, so basically how the data is formatted is they collect the raw data from the telescopes, and then they reduce that data through processing, correlating, and calibrating, basically just overlaying all on top of each other. And then they use 3 different methods for image reconstruction, which are shown over at the side. And that might look familiar to what's been seen in the news a couple of years ago. And so basically those 3 different methods try to reconstruct it. And then we basically put them all together after comparing this raw data to synthetic data, which is kind of how they do the calibrating. We put all these images together, and then that's what we say that's the picture of the black hole. So all of this data is publicly available on the data products page of the Event Horizon Telescope collaboration. So that's already, a point in favor of everything being open source. So what is this project? This project has been me and 4 undergraduate students at the University of Tennessee, Knoxville, who have been trying to do a reproducibility study on this specific black hole. So this is important because this is really important because the reproducibility of this science can basically allow anyone from around the world to basically look at the data and try to find things that the collaboration can't find. I've done a study like this before with LIGO, and through that reproducibility study, we were actually able to identify something that the LIGO consortium hadn't quite. By using different methods, we'd basically been able to find something that the LIGO collaboration itself hadn't been able to verify was a gravitational wave. So basically, when it comes to this, by making everything open source, it allows for people around the world to contribute to the methods that are used to finding these black hole images and basically seeing, hey, is there anything else in this raw data that could be possibly a black hole? And given that we don't know a lot about black holes, it's very important that we are able to find as many as possible so we can study them. So what's the progress then on this project? So we basically took a series of 5 EHT related papers and deconstructed them into a data in brief. This not only helps us better understand the data, but it also gives us a reference as to, what the parameters are, how the data is formatted, and everything that we need to actually make this code so that we can allow people to basically run these methods for themselves. It also gave us the methods that we'd be using, or most of them. And then this data in brief can also help us when compiling a list of things that are publicly available, and then a list of things that we had to figure out on our own. Through the papers, we were basically able to figure out more about the data and, how exactly they did what they did so that we could try to reproduce it. Unfortunately, this led to some challenges because despite coming through these many papers, we had a hard time coming up with the parameters necessary to run the equations. So we found that table right there, which tells us the parameters of each individual facility, each individual telescope. However, that's not really helpful when you have a bunch of equations that have nothing to do with the telescopes. Another thing that we had a bit of trouble with is the public data raw or pre-filtered data. And if it's pre-filtered, then what were those filters? While we found a list of filters in the papers, we don't know if they're already applied or not. So that is something that we have to figure out on our own. Another problem is that we found 3 big methods, and one of them had a dead link, and the other one we were able to find through Google after also realizing that it had a dead link. So this project has come up with a couple of challenges in order to try to figure out, what is going on. However, we have been able to produce some results. So we were able to recreate some of the plots that are based on the baselines of each telescope. And this is important because this basically just tells us, where it's looking in the sky and basically what it's sensing everywhere. So they're very similar to their original counterparts. The original counterpart is on the left side and our data is on the right side. And we've done this for April 5th, 6th, 7th, 8th, 9th, and 10th, which are all the dates that we have data for. This is from back in 2017, which is why it's public data now. And our results are fairly similar, except that they're in different units. So that is something that we are going to have to work on, which is trying to get all these into the correct units so that we can basically compare them. So with all that said, what is the future work? As I touched on before, it would be, converting everything to the correct units. However, we also need to figure out how to compare our plots to those in the paper. We do not have the raw images. We basically just have what the paper has. So we're going to have to figure out how to overlay them or find some other method of comparing the data that is specifically in the papers to the ones that we have. Another thing that we had to do is, as I mentioned before, the calibration involves making synthetic data and comparing it to the raw data. And we need to basically come up with the plots of the synthetic data, which has been something that's been hard to wrap our heads around since not many of us are astrophysicists. Another thing is compiling what is missing, like finding that last method, that's the dead link. And we also need to figure out basically how to implement this so that other scientists can look at what we have done so that they can run these methods for themselves. And then also, last and not least, we need to release the GitHub repo publicly. I don't know if anyone has any questions.
I have a question.
Mm-hmm.
When you're saying you're comparing the raw data to the synthetic data, when you refer to synthetic data, is that like simulation type data?
Yeah, it's basically simulation type data, basically, based on general relativity and what we currently know about black holes. So it's basically what we expect to be seeing.
Okay, thank you.
So Rebecca, you did not mention, so like in order to replicate these results, like what sort of computing do you and the students have to use, or like everything can just be done on one server?
Everything that we've done so far can be done on one server. We haven't found a need to off branch yet. However, we also haven't gotten too far into the imaging processing. Like, as I mentioned before, what we have currently is the baselines for the telescopes, and that's a little bit easier to run rather than, you know, the full basically the 3 imaging methods that I mentioned before, with that basically actually show the black hole. So once we get there, I can kind of better answer that, but currently we've only had to use one server.
So in your judgment, I'm just curious, you may not know the answer. So do you think, like, overall, like even when like the EHT collaboration came out with these first images, did they have to do a lot of processing, or actually it wasn't a lot of processing, but just maybe some correlation of data from the various telescopes that could just be handled? You know, like, as you mentioned, you worked with LIGO before. So, you know, like LIGO was on the opposite end of the spectrum, where like for them to detect anything, they really had to do a lot of processing. So do you have a feeling whether the EHT collaboration in general had to do a lot to even come up with this first image of the black hole?
I honestly, based on reading the papers, I think that they did have to do a lot of processing, especially given that, you know, no one had ever, you know, done anything like that. So yeah, I assume that when they were making the first image that it took a while. I mean, the data for the image was from 2017, and it took them until I think 2019 to actually release it publicly. So
But
I assume throughout all that.
Okay, but their papers don't really mention that, is what you're saying.
Yeah, papers don't really mention how, you know, computationally intensive it is.
Great. Thank you.